Hi, welcome to our work. I'm Insu Kim, working at Samsung Advanced Institute of Technology and also studying at CAST. In this presentation, I'm going to talk about our work, real-world efficient blind motion deblurring via blur pixel discretization. This is about blind motion deblurring using blur pixel classification for building an efficient model. Let me start by introducing what motion blur is. Basically, motion blur images often appears in low-light environments. When capturing the image in the dark, we usually open the shutter in the long time. During the long time exposure, if the camera is shaking or target objects are moving, it leads to significant blur degradation, which is a challenge to overcome. Given a blur image Y, the blind image deblurring procedure finds a sharp image X. Since many combination of sharp image and blur kernel can make the same blur image Y, the blind image deblurring problem is treated as an ill-posed problem. In blind motion deblurring tasks, we can categorize the methods into three types. One is the kernel-based method. The kernel-based methods focus on estimating blur kernels and then using them in the deconvolution process. Finally, the sharp image is estimated. Since it is hard to obtain GT kernels in realistic datasets, those methods usually use the synthesized blur images that may not hold in practice. Recently, the kernel-free methods have been more studied. This method treats the image deblurring tasks as image-to-image translation tasks. So it does not consider blur kernels and just directly predicts sharp images from blur images in realistic blur-sharp pair datasets. Despite its simplicity, those methods achieve state-of-the-art performance, but they highly relies on network capacities or network designs, which may limit to practical usage. Another research direction in deblurring tasks involves utilizing additional self-generated prior information. Those methods are based on kernel-free methods, but they additionally produce self-generated priors and incorporate them into the deblurring procedure. These methods further improve deblurring performance, but generating prior information consumes additional significant computational costs, which makes them less practical for real-world usage. So far, we have discussed the previous methods and their limitations in terms of practical usage. As recent advances in camera technology enable us to capture high-resolution images like 4K images, dealing with large motion in high-resolution images is required nowadays. Also, in order to use the deblurring model in resource-constrained devices like mobile devices, an efficient model capable of handling large motion is necessary. This is our goal in our paper. In our earlier experiments, we found that the small-scale model, we just simply decrease the model size, suffers from significant performance drops in large motion scenarios, as shown in the table. In fact, the small-scale deblurring model, without any prior information, may be susceptible to distortions. Before we go into the details of our method, we first discuss the concept of image residual error. Image residual error refers to the differences between sharp and blur images as shown in the figure. In the deblurring tasks, instead of directly estimating sharp image, we typically estimate this image residual error and then add it to the blur image. Finally, we can get the deblurred image. For this reason, image residual error can be considered as a ground truth. By analyzing and understanding of this ground truth, namely image residual error, we could develop an efficient deblurring algorithms. We will discuss this in the following slides. In this slide, we analyze image residual error and what characteristics are in it. As shown in the figure, in case 1, the left image shows the sharp image, the middle image indicates an object motion blurred image, and the right image is the image residual error. You can see that the object movement regions like person's leg highlight image residual errors when compared to non-moving regions like a flat wall. We realize that image residual error can be characterized and categorized by motion amount or motion types. On the other hand, in case 2, the blur image is uniformly blurred. Despite the same blur for all pixels, it turns out that the high-frequency region-like edges shows high image residual errors rather than those of low-frequency regions like a flat wall. In this case, The image residual error is characterized and categorized based on how complex the neighboring pixels are, I would say, spatial frequency. The image residual error is characterized by its motion type and neighboring pixels. We call this characteristic motion frequency property. So, using this motion frequency property, we can discretize blur pixels and then obtain the discretized image residual error. This brings us to our main idea. In this paper, we rethink the deblurring task by decomposing the original regression problem into blur pixel discretization and discrete to continuous conversion problem for efficient deblurring models. Our intuition is that we build a discrete version of GT like discrete image residual error by identifying blur pixels and then transform it into a continuous form, which is computationally more efficient than naively solving the deblurring regression problem. One thing I would like to emphasize is that we can build the blur pixel discretization model to be efficient because it is based on classification tasks, which is easier than the regression tasks. Before we discuss the details of our method, we introduce some related works here. Since our discrete image residual error is regarded as a self-generated prior information, our method can be interpreted as a type of deblurring methods like deblurring with prior information. MSDINet is one of the deblurring method with prior information. It estimates the degradation representation as prior information and uses it for deblurring and reblurring procedures. However, generating the degradation representation and integrating this into the deblurring procedure is computationally expensive, as indicated in the table. Also, the prior information of this method, like a degradation representation, is not directly related to GT, namely image residual error, which limits performance improvement as shown in the table. UFPNet also estimates prior information by estimating non-uniform kernels. The thing is that generating prior information and fusing it with deblurring procedure requires a huge computational cost, as indicated in the table. Furthermore, although the non-uniform kernels are beneficial, they are not directly related to GT. So the performance of this method lags behind our method. Now, we discuss the details of our method. Our method consists of two stages. In the first stage, we train our classification model, which consists of blur pixel discretizer and kernel estimators. The blur pixel discretizer is optimized to produce the discretized image residual error at a low computational cost, which is referred to as a blur segmentation map. In the second stage, the D2C converter efficiently transforms the blur segmentation map into a continuous form. As a result, our two-stage learning scheme achieves better deblurring performance at a low computation cost. In this slide, we explain our key module, blur classification model. As you can see in the figure, the blur pixel discretizer serves as estimating the blur segmentation map indicated as number 3, which indicates per pixel blur class information. The kernel estimator has a role in predicting several basis kernels indicated as number 1, so that we can obtain several corresponding deconvolved images, which is called deconvolved class images indicated as number 2. Now we have the blur segmentation map and deconvolved class images. Using the blur segmentation map, we perform a pixel-wise sampling from the deconvolved class images to subsequently estimate the deconvolved image indicated as number 4. Finally, the blur segmentation map, like per pixel blur class map, is optimized by minimizing the distance between the deconvolved image and GT sharp image. Here, one thing I would like to emphasize is that non-uniform deblurring inherently involves inoperating deconvolution between motion-related pixel kernels and frequency-related neighboring pixels. So our blur segmentation map is then influenced by this motion frequency property, resulting in a discretized image residual error which visually aligns with the image residual error. We have explained how our classification model works. In this slide, we investigate better implementation of training our classification model. Since the deblurring task is an ill-posed problem, we introduce two key techniques to reduce the ill-posedness. First, we utilize the logarithmic Fourier space to simplify the relationship between blur and sharp images, such that the basis kernels are easily estimated. In spatial domain, the relationship between blur and sharp images is convolution or deconvolution. It can be converted into multiplication or division in the Fourier domain. In order to further simplify this, we take the logarithmic operation in the Fourier domain. Then it can be addition or subtraction in the logarithmic Fourier domain. This simplified relationship enables us to estimate basis kernels more easily. The other technique is that we introduce the latent sharp image. There are many feasible kernel solutions due to its ill-posedness nature. When we use a pair input images like blur and latent sharp images, it helps limit the number of feasible kernel solutions, making our kernel estimator training more easily. So, we introduce an additional loss, directly optimizing the distance between this latent sharp image and sharp image. In the previous slides, we demonstrate that our classification model produces a discretized image residual error under a small computational cost, for example, 4 Gmax. Also, it may allow for less computational cost of the subsequent task like discrete to continuous conversion, because we have a discrete version of GT so that the subsequent deblurring task becomes simple. As a result, we can build an efficient discrete to continuous converter, and the final deblurring performance is still comparable to that of state-of-the-art methods. As shown in the figure, given a blur image, we estimate the blur segmentation map using the frozen blur pixel discretizer. And then we transform this discrete map into a continuous form by our D2C converter. Finally, our D2C converter is optimized by minimizing the distance between deblurred image and GT sharp image. Let's move on to the experimental results. First, we present our blur segmentation map. You can see that our blur segmentation map visually aligns with the image residual error in the case of camera motion and object motion. In this slide, we compare our efficient model with other efficient models like FFT-Former and NAFNet. All models are based on around 16 Gmax by adjusting the channel size. As you can see in the figure, our method gives better visual results than the others. We also compare our method with the commercial applications like Samsung Enhance X and Google Unblur. You can see that our method gives compelling results in real-world scenarios compared to the commercial applications. Also, the on-chip execution time of our method is comparable to those applications. In this slide, we demonstrate the effectiveness of our method in realistic benchmarks like RealBlur, RSBlur, and ReloBlur. The results show that our method outperforms the other methods. In particular, our efficient model, SegDeblur-S, its performance is comparable to that of the larger model, like NAFNet 64. So, our method is up to 4 times computationally more efficient in RealBlur and RSBlur, and 10 times more efficient for ReloBlur. In this slide, we investigate other prior information. Basically, as shown in the right figure, our classification model not only generates a blur segmentation map, denoted as number 4, but also provides a latent sharp image, denoted as number 1, and deconvolved image, denoted as number 3. For continuous prior, we can obtain the latent sharp image and deconvolved image. On the other hand, for discrete prior, we can obtain the corresponding discrete counterpart, like the latent quantization map as indicated number 2, by quantizing the image residual error within the latent sharp image and our blur segmentation map. I would say the blur segmentation map is regarded as a discrete counterpart of the deconvolved image. As shown in the left graph, for continuous prior, the deconvolved image gives better subsequent deblurring performance than that of the latent sharp image. This is because the deconvolved image is influenced by the motion frequency properties, but not the latent sharp image. This means that when we generate prior information, it is important to consider the motion frequency properties. And it is observed that the discrete prior like latent quantization map and blur segmentation map gives slight performance improvement compared to the continuous counterparts like latent sharp image and deconvolved image. We believe that the discrete prior information provides more clear information due to its discrete nature, so that it gives better performance. For more insights on the proposed method, we conduct more experiments and ablation studies. You can check our paper. Thank you.